Hello, I'm Tom Christensen of Neurochrome. In this video, I will show you how to turn these two Modulus-86 revision 3.0 circuit boards into two high-end amplifier modules. The Modulus-86 is one of the lowest distortion amplifiers in the world and it has a super clean sound. Each of these boards requires $50 worth of parts and you can solder it up in an evening. In order to assemble the Modulus-86 circuit board, you'll need some tools. And here they are. You'll need some solder, you'll need a pair of side cutters, you'll need a pair of pliers, ideally like needle nose or flat nose pliers, and you'll need a small flat blade screwdriver, and of course a soldering iron. Alright, so you get your bag of parts, or your box of parts, and I'll be the first to admit that it appears a little intimidating, at first, at least when you're faced with this enormous pile of parts and plastic and whatnot. But let me help you make sense of it. So the first thing I like to do is to sort the parts. I like to have the 1/4 watt resistors separate, ceramic caps in one pile, electrolytic caps in another pile, and diodes in a fourth pile, and everything else sort of back in the box, just to keep track of it. So let's do that. Alright, so now I have all the parts sorted. I have the 1/4 watt resistors in one pile, ceramic caps, diodes, power resistors, electrolytic caps, and basically everything else. So that's connectors, mounting brackets, IC sockets, and then the remaining semiconductors. One trick that I like to use is to use a binder clip like this to hold the parts together. They are pretty cheap from any office supply store. That makes it possible to toss these in the pile and you don't have stuff mixing. Okay, so now that we have the components organized, let's talk a little bit about the order of assembly for the circuit board. You need to take three variables into consideration. One is the heat tolerance of the parts. The other is the ESD susceptibility of the parts. ESD stands for electrostatic discharge. That's a lengthy and complicated topic that I'll cover in a separate video at one point. And the final variable is the height of the part. Just like when you're building a house, it's easiest to start with the foundation and work your way up. And similarly with a circuit board, it's easiest to assemble it if you start with the lowest components first and then finish off with the tallest components such as electrolytic capacitors and so on. So basically what I prefer to do is to start with the parts that can tolerate the most heat, because as you solder the circuit board, you expose it repeatedly to heat, and if the most heat tolerant parts go on the board first, you have the greatest chance of them surviving the soldering process. So heat tolerant parts would be stuff like 1/4 watt resistors or resistors in general, ceramic capacitors, IC sockets and connectors, that sort of thing. So I start with the 1/4 watt resistors, I work my way up to the ceramic caps, then I typically do the diodes because they tend to be low to the board, then I follow that with power resistors, connectors, and then finally the semiconductors other than diodes. So ICs, transistors, and that sort of thing. Alright, so let's solder up the 1/4 watt resistors. You'll notice on the bill of materials that there are quite a few different values of resistors in this board. What I prefer to do is to grab one value and then work my way through that. So if that happens to be, say, R1, R4, and R7 that are all, say, 100 ohms, then I populate 100 ohms in those three spots and I move on to the next value. For me, that's easier rather than trying to populate the parts sequentially, R1, R2, R3, R4. But you can do it however you like as long as the parts get in the right spots. So rather than bending the component leads by hand, I prefer to use pliers. And if you hold the board such that the component is over the desired footprint and then grab it right at the inside edge of the hole, then bend like that, and stick it back in the footprint, grab it on the other side, right right at the edge of the hole. Bend. Now you will find that it fits perfectly in the board. So, like that. And with practice, once you get to know your tools pretty well, it's pretty easy just to get the spacing right. Like that. So this blue anti-static mat is a bit sensitive to heat, so I use an old circuit board between the PCB that I'm working on and the grounded anti-static mat. This one. And two. And then you just cut the leads off. There's some controversy around whether you should cut the leads before soldering or after, but I'm not sure it makes a huge difference. I'm just pointing out that there is some controversy. The theory is that the shock of cutting the lead is enough to sort of disturb the solder joint. So what I often do is I populate all the parts and then I cut all the leads and then I solder. So I'll do that for the next couple of resistors here. When you cut the leads, leave about 2 millimeters sticking out of the board, just enough to solder to. And now let's repeat for the second board. The reason I bend the leads over a little bit is to prevent the resistors from falling out when I turn the board over. Like that. So I guess there's no need for you to sit and watch me solder 20 some resistors. So I'll leave you to it and I'll be right back. Okay, so now it's time for the ceramic capacitors. Now with these, it's important that you go value by value because if you just pour them all in a pile, they are almost impossible to tell apart. They do have a code written on them, but it's light gray on light blue and there's hardly any contrast. It's hard to read. So be careful. You do want to make sure you get the capacitors in the right spots. Just go one value at a time. So the ceramic caps are a bit easier. because they have the proper pin spacing. So all you have to do is drop them in the footprint. There's no need to bend leads or anything. Just drop them in, bend the leads on the bottom about 45 degrees so the caps don't drop back out, and solder, and you're good to go. Now with the ceramic caps, I do tend to just leave the pins sticking out and then cutting them all off at the end. They're all the same length, so it's pretty easy, and they're usually not in the way. So now let's go ahead and populate the rest of the ceramic caps. Okay, so now it's time for the IC sockets. And as some of you may have noticed, I'm not using anything to hold the circuit board like a third hand or whatever. What I like to do is just put a little bit of pressure on the board with my pinky as I solder, and that prevents the board from sliding. But it does make it a little more cumbersome to solder IC sockets. What I like to do is I leave the solder overhanging the workbench by a little bit, and then I drop the socket in the board where I want it. I make sure that the notch in the socket is aligned with pin 1 on the board, and then I just hold on with one finger on one side and solder one of the pins that I'm not touching. Just like that. Oh, come on. Ta-da! And it's tacked in place. Now I just need to finish the remaining 7 pins and I'm good to go. So next up are the 2 power resistors. The easiest way I find to solder the power resistors to get the right pin spacing on them is to overlay them on the footprint, then grab the pin so that the edge of the pliers is lined up with the inside of the hole, and then just bend the pin over. Stick it in the footprint, and grab the pin so that the inside, or the outside of the pliers are aligned with the inside of the hole in the footprint, and then you just bend it over. And then it drops right in, like that. You do want the resistors lifted up a little bit from the board so that air can pass underneath it. Doesn't have to be super critical what the dimension is, but leave a couple 3 millimeters maybe, like that. So now the resistor can breathe a bit. And to prevent the resistor from being pushed up against the board, I just lay it on top of the pliers so that the resistor just drops naturally down. And solder. And that's all there is to that. Then just repeat with the second power resistor and off to the next. So next up are the diodes. Just remove them from the tape. Note that diodes are polarized. So they are marked, their cathode is marked by this colored band, and that needs to be aligned with the corresponding lines of on the diode footprint on the board. So since there are already components on the board, it may be easier to flip it upside down. Then place the diode over the footprint, align the pliers with the inside of the hole, and bend the pin over. Then stab the pin through the board. Again, grab the pin by the inside of the hole and bend it over. And then it drops right in. Now you just have to repeat that 7 more times and you're good to go. Next up are the electrolytic capacitors. Do note that the electrolytic caps are polarized, so they are marked with a white band, in this case for the minus end of it, or the cathode, and on the board is a little plus for the plus end. So let's align the minus with minus, ta-da, like that. Just turn it over, bend the pins, and now we're ready to solder. Alright, so we're almost there. Now I need to put in the inductors. I do make these, or rather I have them made by a company in the US, and they do a really nice job, but they are a bit pricey. If you would rather wind your own, you need about a meter of 18 gauge transformer wire, or enameled wire, and I provide the instructions for how to make the inductors in the design documentation that you will receive when your order ships. But the ready-made inductors are nice in that they just drop straight into the board and all you have to do is solder and you're done. So let's get the inductors in, and I'll also install the connectors and the 2 mounting brackets. The final pieces missing are the 2 voltage regulators. So let's install those. One thing you need to know about these is that they have sort of a D-shaped package, and the flat on the D-shape needs to align with the corresponding flat on the footprint on the board. And there you have it. Now all that's left to do is to install the 2 8-pin ICs in their sockets and install the LM3886. And of course to mount the finished module to a heatsink. The easiest way to mount the LM3886 and to get it to line up properly with the holes in the heatsink is to mount the board in the chassis and mount the LM3886 on the heatsink. Then tack solder a couple of the pins from the top, unmount the board, and then solder the remaining pins on the LM3886. It's a little cumbersome, it takes a bit more time, but I find that method works really well for getting everything aligned properly. Alright, so now it's time to plug in the 2 8-pin ICs, the LM4562s, and then dry fit the board and the chassis. One issue with the 8-pin ICs is that the pins are actually spaced such that they don't quite fit in the socket directly. The pins need to be bent a little bit. So I will do that by gently rolling the IC just a little bit. Like that. And then align pin 1, push it in. And do that again for the next one. Like that. You do want to make sure that all the pins get into the proper holes in the socket. Sometimes what tends to happen is that they sort of fold under, so you don't want that to happen. Okay, so now I just have to do the second board, and then we're good for the chassis work. Let's put the boards in the chassis. So I have here a quite nice chassis, obviously half assembled, but it's made in Japan. I designed where I wanted the holes placed, where I wanted the boards. So this is sort of a universal chassis. It'll take the Modulus-86. It'll take revision 3.0, I should say. It'll take the Modulus-186 and the 286. It also has holes for the ISS, the Intelligent Soft Start, so that I can control the mains power. And there's room for a fairly sizable toroidal transformer and the Power 86 and Power 686. So that should be a pretty nice amplifier. The heatsink I already had drilled and tapped for the Modulus-86 and the other amplifiers. So the board really should just drop straight in and all be good to go. I'm using some 10mm standoffs to attach to the two holes along the front edge of the Modulus-86. The rest will attach on the heatsink. Alright, so let's get started here. So I'll attach one board along the heatsink like that. First screw is always a little bit of a pain to get started. Oh, come on. There we go. I'll leave it just a little bit loose. And then the second screw, just finger tight. And the angle bracket. See, this is why you want to leave it a little bit loose, so you have a little bit of slop to work with. There we go. And final. So I'll just tighten these up. Like so. And now it's time for the LM3886. So it should just drop straight into the board. Ta-da, like that. And mount with a screw to the heatsink. Yay! Like that. Of course, for the final assembly, you want to use a little bit of thermal paste on the back of the LM3886. But for this dry fit, the purpose is to get the LM3886 in the right spot. So for this, I'll just assemble it without the thermal paste, get the LM3886 soldered, and then when I assemble the complete amplifier, I will then add a little bit of thermal paste on the back of the LM3886. You don't need a lot. Just enough to sort of cover the voids. What I often do is I smear it with a finger, and then I take the sharp edge of a knife blade and just sort of shave off the excess, and that's plenty. You really just want the voids to be filled because the thermal grease is not very thermally conductive, but it's a lot more thermally conductive than air. And now let's solder the LM3886. So I really just want to tack it in place. So I'll try to hit at least one pin in the row that's closest to the heatsink and 2-3 pins along the front. That gives it enough stability that I can take the board out and then solder properly from the bottom. When you solder that 1 or 2 pins in the back row there, in the row closest to the heatsink, be a little careful that you don't accidentally create a solder bridge between the pins, because that's likely to destroy the LM3886. So just inspect it carefully after you're done to make sure that there's no solder that connects the pins. And now let's get it soldered. It's probably not a perfect solder job, but once I finish it up from the bottom, it'll be just fine. So now I just need to solder the LM3886 from the bottom of the board. Just like that. Now I just need to repeat the process for the second board. Cool. So I just got done washing the flux off the board, and now it's time for the final test. If you're curious about why I cleaned the flux off the board, check out my video on the topic. So the first point in the test is to power up the board with a current limited supply. If you don't have a current limited supply, you can insert a 10 ohm resistor in series with the plus and the minus. If you have an issue with the amplifier circuit, those resistors will go up in smoke. If you do have a current limited supply, I recommend using it and set it for like plus minus 20 volts at least. No more than plus minus 42, but plus minus 20 is about good. And if you run the Modulus-86 without a load, so no speaker attached, you can run it without a heatsink. The LM3886 does get a little bit warm, but it'll be just fine. Under those conditions, the board draws about 85 milliamps. So that's what I have going on here behind me. The Modulus-86 is powered by an HP 6237B lab power supply. It's a tried and true laboratory supply. You can find them on eBay for not that much money. And if you find one that's in decent shape, I recommend picking it up. So let's measure the DC offset of the Modulus-86. So I have the input shorted with a shorting plug, and I'm simply going to power the amp up under those conditions and measure the DC voltage on the output. And the DC voltage on the output measures about 420 microvolts. So that's excellent. Now let's check the gain of the amplifier. I recommend using 400 Hertz at 100 millivolts. The reason I recommend 400 Hertz is that most handheld meters, which I'm assuming that most of you have, don't have very wide bandwidth, but they can usually measure up to 480, 500 Hertz at least. Benchtop meters tend to go way wider. Mine go up to about a megahertz. So 400 Hertz, aim for about 100 millivolts in. If you don't have a signal generator, you can use a media player and just create a test tone with the proper frequency and amplitude. Then adjust the volume control so that you get 100 millivolts roughly on the input of the amplifier. So now let's measure the gain. So first I'll put the meter in AC. I'll check the input voltage. It measures 101.5 millivolts, so I will expect, I mean, the amplifier has a gain of 10, so I should expect 1.015 volts out. Let's measure that. 1.014. Done. So if the amplifier has the proper gain, it has low DC offset, plug it into a test speaker and see if it also sounds good. I'm assuming that most of you don't have access to a distortion analyzer, and that's fine. I have done the hard work for you, so if it works up until this point, then you're golden. So congratulations on the build, well done, and thanks for watching. If you found this video informative or helpful, please click the like and the subscribe button, and if you haven't already, I strongly suggest you buy one of my circuit boards. Thank you. Have a good day.